So I'm going to talk about, this is going to be a statistical mechanics talk. I'm going to talk about the Wei model, which I will define, and this is joint work with Paul Dario, who is in Paris. So this talk is about one particular model called Wei model, but in fact, there's a class of models in statistical mechanics that I want to mention. It's called abelian spin models, which means they're statistical mechanics model so that the spin configuration is belonging to some abelian group. So there are other examples in this class of models, and including XY or abelian gauge theory and so on. And the lane is a special example, but as you will see that in many of these models, there is this very nice feature that there's a duality for the spin model to a Coulomb gas and a height function. And then we can combine with the tools from renormalization and especially from homogenization of PDE to get very precise limits about the symptotic behavior of these models. Okay, so let's start by introducing the well-known XY model, which is the model such that the spin takes value on the unit circle. So at every side there's a spin on the unit circle. So the XY model is easily defined by, you can look at the Gibbs measure so that the interaction is given by the nearest neighbor in a product. And also because the spins are on the unit circle, this is, you can parameterize it as cosine and sine. And therefore, this is also equivalent to the sum of cosine of the difference of angles. And the first natural observation here is that if your beta is large, if you have low temperature behavior, then the spins next to each other tend to align with each other. So that's what happened in XY model. So as we will see that this model has very special kind of phase transition, and so it's kind of used a lot in modeling low-dimensional materials. And I'm also giving just a very quick remark that we have defined the Gibbs measure on a finite graph lambda, but it's easy to see, well, it's not easy, but nowadays it's well known that there is some multiplicity result which due to Geneve, so that you can actually also have a well-defined limit in the infinite volume, and that's going to be the measure we are focused on. Okay, so now similar to the XY model, Villain, who is a physicist, proposed the following statistical mechanics model. It's something like an approximation of the XY model. So the idea is that if beta is very large, well, as we said, the beta large means the spin tend to align with each other, so the theta I minus theta j is small. So you can actually approximate this XY interaction in terms of this heat kernel on the S1. So this is approximately equal to, this is some kind of, it's like Gaussian, but it's periodized over the circle, right? So you have to sum over all possible windings of these Gaussian. So this is the heat kernel on the unit circle. And if you go back to the XY and you replace each interaction here by this heat kernel, and what you get is a new measure which is called the Wei model. So this is the definition of the Wei model. Now, what do we know about these models? So in fact, the reason that XY and Wei received a special attention is that they have some kind of very special type of phase transitions. So unlike the usual materials like a ferromagnetic, that you have some symmetry breaking under, during the phase transition. What's special there is that in 2 dimensions, continuous symmetry is not going to be broken at any temperature, and in fact, it's kind of a well-known phase transition of the Kosterlitz-Thouless type, which can only be distinguished by looking at the topological defects, which are vortices that we're going to mention. And in dimensions 3 and higher, there is a symmetry breaking, meaning that these spins do have a preferred direction at low temperature, but there will be a macroscopic fluctuations because it's kind of spin model with a continuous symmetry, and these macroscopic fluctuations is something believed to be given by a spin wave, which is a Gaussian free field in a way, in dimension 3 and higher. Okay, so let's move to what was known and what was conjecture. Okay, so let's look at what happens in dimension 3 and higher. So the first rigorous result is by using the so-called reflection positivity trick. So this is the result in the 70s, Froelich, Simon, and Spencer, who showed that if you look at the asymptotic two-point function, two-point correlations, as x goes to infinity, then this quantity has a uniform lower bound, which is 1. So this G0 is just the Green's function for simple random walk in ZD, which is in fact a finite quantity when dimension is larger than or equal to 3. And therefore, when beta is large, we see that this has a lower bound, which is uniformly positive. Okay, so that's the long-range order for the XY model in dimension 3 and higher. And the next question you could ask is, what's the next order, right? If you sort of subtracting the leading constant, what do you expect? So here is a physics argument, sometimes called a spin wave, which suggests the following. So if we believe that at very low temperature, the angle difference is small, then the first order perturbation theory gave you that the cosine is just a quadratic function. And then you can just replace everything by a Gaussian free field, if you believe the heuristics. And for Gaussian free field, it's very easy to compute, right? So the two-point function, which is this e to the I of, okay, the inner product is given by e to the I of theta 0 minus theta x. Then for the Gaussian, you can compute it in terms of the Green's function. And the Green's function computation what gave you that in 2 dimensions, there is a logarithmic difference. So what you get is x to the minus some power, 1 minus 2 pi beta. And in dimension larger than or equal to 3, and the Green's function differs, it's going to be a power law decay. And therefore, you would expect there's a leading term, which is of order 1. There is next term, which is 1 over x to the d minus 2. Okay. However, we will see that this very simple kind of spin wave argument is qualitatively correct, but quantitatively not correct. So the exponent, so we got here is not the right exponent, and the constant you got it here and here are not the right constant. Yes?
If G0 is a finite number.
So that is, well, it depends on, so in 2D, this is like some potential kernel, so only the difference is well defined, but in 3D, certainly the Green's function is, this is like just simple random walk Green's function. Right. So in 2D, only the difference makes sense, but in 3D, each term is well defined. Okay, so the reason that this spin wave is not very precise is the reason is it neglects the occurrence of the vortices. As we see that in a spin system with this, take a value in U1, there will be vortices, there will be anti-vortices at some point, and these vortices would actually interact and change the behavior of the two-point function. In fact, so here the first non-rigorous treatment of the vortices is going back to Kosterlitz and Thouless, and what they do is they want to decompose the spin into a vortex-free part, which is more like a free field that we discussed in the spin wave approximation, and a vortex contribution. And they have a heuristic argument saying that the vortex contribution is in fact turned out to be independent of the free field, and it interacts like a neutral Coulomb gas. So it's a two-dimensional argument, and they argue that the vortices behave like a neutral Coulomb gas. Okay, later we will see a rigorous version of this derivation that, in fact, for the Villain model, not XY, but the Villain model, you indeed have this decomposition into a Gaussian free field and a vortex, and that's also known, and that's exact. So this, okay, they allow, I mean, this kind of observation allows Kosterlitz and Thouless to write down the famous KT flow to study the scaling behavior of the neutral Coulomb gas, and they write down this very famous ODE called the Kosterlitz-Thouless flow, which gave you the scaling limit in the 2 dimensions. So let me just mention some of the known and unknown results in 2 dimensions. So first of all, this Kosterlitz and Thouless predict that for any temperature which is larger than the critical one in the KT phase, the 2-point function would asymptotically have an exponent, but the beta effective does not equal to the beta. Right. If you have 1 over 2 pi beta, that is the calculation we see before from the spin wave or the Gaussian approximation, but the vortex would actually enter into the picture and change the effective beta. So this still remains open until now. And okay, what was known is that there are upper bounds. So first, in the 70s work by McBride and Spencer, who got this, it's a very short and elegant argument, who actually find an upper bound of the Gaussian type. So the 2-point function is bounded above by what you get from a spin wave calculation. And more recently, Abellio and Galvin has improvement of this exponent. So now, in terms of the lower bound, there is this work of Froelich and Spencer, who used the multi-scale argument, showing that for very low temperature, the 2-point function has a lower bound, but the upper and lower bound does not match. So far, this asymptotic exponent is still open for the 2dxy model. Yes.
I actually think that they don't even have beta to the -1. I think they have beta to a wrong power.
Yeah, so some beta minus.
They have the correct one for Villain, but the wrong one for.
Maybe Abellio has the right one, right?
We expect it.
Okay, yes. I guess in the McBride Spencer paper, they probably have.
No, in the lower bound.
In the lower bound.
I think they have. There exists a positive power such that you get beta tilde to this positive power, I believe.
Yes, but I think there's some more recent review which says if you investigate in that proof, you find it's like multiplicative of little of 1. It's like, okay, the difference is not small, but multiplicatively small, basically. There's some review.
Okay, maybe we discuss. I would be interested.
Yeah, okay, there's some review by Ron Pellet, for example, who has.
That is for Villain again.
I think that's for Villain.
It is for Villain, yes.
Ah, yeah.
Yes.
Ah, okay. No, I think that the other power is for XY model.
Okay, so
These are results for XY model or Villain?
These are for
well, I think when you have this in the original paper of Froelich and Spencer,
several
they
results
for both cases. Now in the review paper of Pellet, I think they wrote it for Villain. Yes.
Yeah, I think they have it for
Yes. Okay. Maybe there is. Yes. Okay. Sure. Right. So that's the upper and lower bound, and this question still remains open in 2 dimensions. For related models, this kind of asymptotics has been proved. Maybe let me just briefly mention that for one example is the 2-component neutral Coulomb gas, which Falco studied. It's a neutral Coulomb gas with sufficiently small activity, and he can actually rigorously prove that the correlation function has this particular asymptotic behavior for beta larger than the critical temperature. And and another example is the so-called discrete Gaussian model. It's a random height function, integer values, and through the work of Bauer-Schmidt, Park, and Rodriguez, we know that the temperature is small enough, the field converges to some Gaussian free field with some effective covariance. So these are the two examples that questions of the same type has been solved, but the question for the xy in 2D is theorem is open. Okay. Now let's move to dimension 3 and higher. So indeed, as we suggest that the spin wave calculation gives the wrong constant. So the conjecture would be that if you look at the next order for the two-point function, which means you're looking at the truncated two-point function, it will have a leading term which is constant over x to the d minus 2 plus a lower order term, and the effective constant is different from the one you get from Gaussian computation. So there are some partial progress toward this in the 80s. So first of all, there's a paper of Frolic and Spencer which gives upper and lower bound of the two-point function, which does not match with each other. And then this paper, Brickman, Fontaine, Lebowitz, Deep, and Spencer, they studied the so-called transversal two-point functions. So what they did is you can look at a Gibbs state for the XY model, which is in a finite volume, you just have all your spins pointing to the one particular direction. So you have a boundary condition with all spins pointing to one direction. You took the infinite volume limit, so that gives you some Gibbs state. And now if you look at the transversal direction, right, the second component of spins, and that gave you the sine-sine correlations. So what they have proved is that the two-point function has the upper-lower bound, okay, differ by some multiplicative constant at room temperature. Now, in the broader picture, these results fall into, in 3 dimensions, fall into the so-called Goldstone theorem, which actually applies more generality, such as the quantum field theory. So what was suggesting is that if you have a model with ON symmetry, and if you have a symmetry breaking in one direction, then in all the other directions, you should have n-1 Goldstone bosons, which is n-1 different free fields appear. And moreover, if you look at the truncated function of the type phi squared x, phi squared y, right, this should be like, if you believe there's a Gaussian fluctuation, this should behave like phi x, phi y squared, which actually gave you 1 over x minus y twice of d minus 2. Instead of 1 over x minus y, d minus 2. So the study of this Goldstone theorem was perhaps, the earliest work was perhaps from Szymanczyk, who studied that in the context of the Euclidean field theory. And Balaban has, in the 80s and 90s, proposed a different approach, which is based on renormalization group. And he studied a class of model which is called n-vector model, which is quite similar to what we have been discussed so far. And he also claimed that the two-point function and vertex n-vector model, truncated two-point function, has this asymptotic behavior of 1 over x to the d minus 2 plus a lower order correction. And Giuliani and Ott has extended this previous result of Brickmo and this result of the 5 author paper to the case of the ON model. And in particular, they can obtain the asymptotic extension of the magnetization at low temperature, but extending this result to the ON models. Now, as we said, that this prediction of the Goldstone theorem telling you that, right, there's a phi square truncated correlation is like 1 over x minus y to the 2 times d minus 2. The analogous object in these spin models, in the case of the Villain or the xy model, would be the parallel two-point function, which means that if you look at cosine and cosine, and minus the truncation. Now, if we believe that cosine theta is about 1/2 times theta squared, this would be the corresponding object like this. Okay, so people believe that the cosine truncated one should decay twice faster than 1 over x to the d minus 2. But the paper in the 80s where they have kind of a right lower bound, but the upper bound is off, right, by a factor of 2. So the lower bound is actually done by some quite generic correlation inequality argument of Dunlop and Newman. But upper bound they can get is still 1 over x to the d minus 2. And in the work of Balaban and O'Carroll, they have a different argument using the normalization group, and they can improve the upper bound a little bit to the 1 over x e minus 2 plus a small constant. Okay, so what we did with Paul is we're trying to study all these questions in the context of the Villain model at low temperature. So in the paper with Paul, which finally appeared last year, we have studied the truncated two-point function for the Villain model, dimension at least 3 at low temperature, and we have give a very quantitative description of the truncated two-point function, namely as it's conjectured that there is an effective constant divided by x to the d minus 2 plus a lower order term, which we have some control. And moreover, we also studied the transversal spin wave, as we discussed in the earlier slide. We showed that the transversal spin wave is like a constant over x d minus 2 plus a lower order correction. So the constant here is different from the one you can obtain from the Gaussian, but it's actually a small correction. So the difference is just, it's going to be a very small difference of order e to the minus beta, when beta is big.
So C1 over beta would be the first term.
This one would be the Gaussian term. So this C effective is not going to be this one, but
yeah, what is C1 for you? C1 is the first term? You said CF is not equal to the constant?
Yes, C1 is the first term, yes.
Okay. So you're saying they differ by this exponentially small correction?
Yes, that's right. Okay, so now they're left with the question of the parallel spin wave and what we can do. So this is a paper in preparation in that we study the parallel spin wave for the Villain in 3 dimensions, and we have almost obtained the optimal upper and lower bounds, except a logarithmic corrections. So the upper bound is different from the lower bound by a power of log. We have not tried to optimize over the log at this moment. So at present, there's this power of log, which is 22. Okay. Okay, so that's all the. Okay, so in the remaining time, maybe I'm going to give a quick explanation of what kind of tools we have used in all these proofs. With a focus, of course, on the first result, but maybe I'll take a little bit of time to explain what was needed for the second result. And so the proof is actually a combination of
Just on the results, so the first one was for all d bigger than 3, and the second one is just for 3?
Yes, this is only for 3, and for d larger than 3, we have improved this, okay, for d larger than 3, we improved this bound, but we don't really get twice as much. Yes. So the proof starts with the duality argument, which I'll explain that from the spin model, there's a duality to the Coulomb gas, and then from the Coulomb gas, there is a mapping to the height function, but it's a vector-valued height function. And finally, we borrowed the tools from the so-called Helfrich-Sjöstrand representation and from the PDE to analyze the scaling behavior of these random height functions. So the first part is actually quite classical. So short description is that you can actually write the Villain in terms of a Gaussian free field times the Coulomb gas. And then you just need to analyze the Coulomb gas part. So how does that work? Unfortunately, since we're in dimension 3 and higher, we have to talk about differential forms, but I'm trying to not talk about it. So I'm just telling you that there are differential forms. There are 1 form, 2 form, 3 form. 2 form are kind of important, which are sort of living on the faces, and all the so-called vortices are living on the faces. Right? So along each plaquette, there will be a vortex, and there will be a d and d star operator. There will be a Laplacian which maps k form to the k form. But in fact, in our analysis, we're gonna not using the forms, but using vector-valued functions, right? For example, if you have a 1 form, there's a natural way to map it, let's say in Z3, to a vector with 3 components. This is just a very natural map. So instead of dealing with forms, we're dealing with vector-valued functions. And of course, you can define gradient, maps k form to k plus 1 form, divergence, and Laplacian, all in the context of the vector-valued functions. And what was important here for the duality is this Helmholtz-Hodge decomposition, which says that you can write a vector field. If it's in 3, you can write it as a potential field, which is co-free, plus a divergence-free field. And the divergence-free field, because you can actually solve it, because this is potential co-free, so you can solve it using the formula at the bottom. And in fact, this is an orthogonal decomposition because when you square it, one term is divergence free, so they're actually the cross term gonna vanish. So now, if we look into the Villain model, you can first, on every edge I have a sum of integers, and I can first exchange the sum and product. So I have a big summation outside, which is you have basically you have a 1 form outside, and what you have inside is here, is the product. And now let's do the Helmholtz-Hodge for this 1 form M. Okay, I'm going to split the sum of all the 1 form by group them first into the Q, which are the vortices, And then I sum over M, which give you the corresponding vortex configurations. Okay? So now if I do that, I can just represent such M so that your curl is a given Q by this Hodge decomposition into a gradient field plus a divergence-free field, which is explicit. Okay? Now, what's more important is that if you plug it back, the special form of Villain, which is the quadratic on the exponential, telling you that these two parts were actually independent. The cross term vanishes, so you have this potential part and this kind of divergence-free part. And by some integration by parts, you will see that this term actually gave you the GFF, and this term gave you a Coulomb gas. Now, the one kind of remark here is that this Coulomb gas has this divergence Q equal to 0 condition, and that's how things differ between 2 dimension and the 3 and higher dimensions. So in 2D, this divergence equal to 0 just means that this Coulomb gas is totally neutral, but in dimension 3 and higher, it actually gave you some local cancellation condition, which makes the analysis easier to carry out than 2 dimensions. Well, the next step is going to be a so-called one-step renormalization that maps this Coulomb part into a height function part. So the basic idea is that this is called Steingolden representation, is that the Coulomb is just the expectation of GFF. Right? Covariance is just Laplacian inverse, so I can write it into some expectation of GFF. And also, we can also run the previous steps, not just having z, but we can also look at the 2-point functions. You can also have some object coming out of the 2-point functions, which is some 2-point functions of GFF times the ratio of 2 partition functions, where the one above basically is like a Coulomb, but have a positive source and negative source. Okay, there's a difference of the 2 Green's functions, so you can also write it in terms of some GFF expectations. And now with the GFF expectations, you can do some one-step renormalization so that you can just decompose it into a local field and a smooth field. So now what is helpful is that in the local field, you can actually first integrate out the local field, and you see that integrating out the local field would give you some kind of decaying quantity in Q. So integrating out the local field would actually give you this factor, which telling you that if beta is big, the Q would have to be having a small support. Okay, and then you have something in the smooth field. So in dimensions 3 and higher, actually one can rewrite this divergence Q equal to 0 condition into into some kind of lattice animals. You can sort of group them into connected components, and if this weight is really small, then you can do some kind of polymer expansion or cluster expansion trick to rewrite everything into the sum of Q, which is the connected configuration of charges. So this is going to be in fact, you can get some ratio of the 2 expectation of the smooth field of these functionals, and the Z is going to be inherited from this kind of decaying term, and we have some bound that Z is going to be decaying in terms of the support of Q. And now from here, one way to write it into a measure is I'm doing change of measure, right? I'm just calling the smooth Gaussian plus this the new measure, and I can use the cosine A plus B to write everything into an expectation of that new measure. So that's the answer. So this is the new measure, which is the smooth field, plus what's happening on the denominator, and then I have some stuff that we need to analyze. Okay, so it looks very complicated. It is complicated, but it's still more tractable than the original Willing model or the Coulomb gas. Is that if you look at this thing, this mu beta, what you see is that the leading term is going to be this Gaussian term, right? There are this term and this term, but as beta gets large, this is going to be acting as a higher order than the Gaussian term, and this z we know has an exponential minus square root beta, so this is also going to be much smaller than first term. So in fact, it's going to be, first of all, it's going to be just a gradient type field because the Q has this neutral condition, and moreover, it's going to be some perturbation of the Gaussian. So you have Gaussian term, and the rest is going to be smaller compared to the Gaussian term. Now we need to study this measure. This measure doesn't look too horrible, but then we have this complicated object that we need to evaluate under the measure. And
So this gradient to the m is what? What does it mean? It's just application of gradient n times, or what?
yes,
Yeah.
discrete gradient, yes. I mean, just kind of expanding out the covariance of that smooth field, you have a higher order derivative. Yes. Yes. Yeah, it's not too worrying this time, but then the object here is very non-local and very non-linear, so we have to understand this well. So we're doing that from the tool of PDE, and in particular from the so-called quantitative homogenization, which, well, basically we're more like adapting the work of Armstrong, Kusi, and Murat to analyze this random height function. So let me give a simple example, much simpler than the measure we wrote. So this is called a gradient phi model. So what is the gradient phi model? So if you have a Gibbs measure which is real valued, and if you have a grad phi squared, that is the Gaussian free field, but the gradient phi model is just replace the grad phi squared by a uniformly convex function that has assumed that the second derivative is bounded above and below. Now, for Gaussian free field, everything is computable, like the two-point function is just the Green's function and so on. But in fact, there's a whole story for the gradient phi model of this type, in that the two-point function also has a formula, but not the usual simple random walk Green's function, but the more complicated one. So let me, so it's here, okay. So basically, the two-point function, if you look at the gradient phi model, is going to be some kind of annealed Green's function. And this is the Green's function not really associated to the Laplacian, but to a more complicated operator, which I wrote L here. This is the Helfer-Sjöström operator. So what is this guy? So this has this Witten Laplacian part. And the Witten Laplacian is defined. So first of all, we can define the gradient, the partial of x, which is just differentiate the field at phi x. We can look at its adjoint in terms of the Gibbs measure, which has this particular formula. And this Witten Laplacian is just the sum of partial x star partial x. It's an elliptic operator. It is self-adjoint if you look at the expectation with respect to the Gibbs measure. So this is the Witten Laplacian operator. And on top of that, there will be another term, which is the more usual elliptic operator when you see a PDE. So this is an operator which has a discrete divergence. And A of grad phi is the second derivative of B times grad phi, times the gradient. Okay, so the good thing is that if V is uniformly convex, then both parts are uniformly elliptic. So there are more tools from PDEs that we can use to study the behavior of the model. And so this is the helpful Hausdorff. This Green's function here is the Green's function of this operator. Okay. And in fact, there's a more general statement which says if you have a function of your phi, a function of random field f, another function of random field g, you can actually compute the covariance by looking at this. Right? There's a more general formula that can give you the covariance for very general functions of phi. So there's a representation which is a starting point for analysis. Now, how do we analyze that? Well, you see that because the covariance structure of the grad phi can be written into some Green's function of some equation, right? So we can actually just translate everything to a PDE question. How do you understand the Green's function of that equation? And in fact, that's how what was called the homogenization comes into picture, is that in order to study the scaling limit of these grad phi type of models, we can start by looking at the Green's function associated with this L operator, which is an operator which is elliptic, but the coefficient has random field, right? We see that there's a V second derivative in the coefficient, and we want to say that in the scaling limit, the Green's function will get very close to some A bar Green's function in RD, not ZD, okay, in RD. So this is a statement in homogenization which says that on large scales, if you have a PDE which has a random coefficient, but on large scale it's well approximated by a solution of a PDE with constant coefficient, which is telling you the effective behavior of the solution. And we're not using any renormalization group, but this homogenization, in a way, does the renormalization for us, right? We encode the information of our Gibbs measure into the equation here, and the PDE argument from homogenization telling us that there is a way that this thing would go into a scaling limit. So that's sort of our way of doing renormalization. In fact, so let me, maybe trying to do a little bit calculation here is that, okay, maybe it's a bit heavy, but we have this very complicated thing here. I want to simplify it and just showing why this is helpful. And so I have this sine and sine, and here I'm going to drop the second term. I'm just looking at the sine and the sine term, and I'm going to do something which is quite heuristic, because we said that at very low temperature, you have this thing is exponentially decaying in the support of Q, right? So I'm just going to replace Q by a so-called dipole gas, which only has a +1 and -1 neighboring to each other. But in the real analysis, in the paper, we're actually dealing with everything. But let's look at this very simplified case here. I'm having some object which I just replaced into dipole here. Okay, and if I'm looking at the truncated two-point function, I can rewrite into a covariance. So this is kind of the covariance in approximation we have to look at. So here I already assume everything is a dipole, so you have to, so instead of summing over Q, you just sum over nearest neighbor, which is a gradient. Okay, which is +or -1, which is a gradient. And so how do we study this covariance? Well, let's apply the Hausdorff formula before, because it can be used to study the covariance of any two functions of phi's. So you just apply Hausdorff, and you see that there are a lot of terms popping up. Now, except the exponential term here, there will be some Well, you have to take derivative here, you have to take phi derivative here. So in the end, you would gain some second gradient of the Helmholtz-Thurstrand Green's function. And the goal is to see that everything what goes to the right quantity, which is the effective constant, divided by beta to the x to the d minus 2, we have to show that the second order Green's function asymptotically behave like a second order standard Green's function. So in fact, this is one of the statements we have proved in our paper, that you have to show that the mixed derivative of the Helmholtz-Thurstrand Green's function is approximately equal to the mixed derivative of the standard Green's function with a control of the error term. Okay, how do we do that? Let me just be very brief. So we're going to follow this approach of quantitative homogenization through the works of Armstrong, Kusi, and Murat. And the way is that we know that elliptic equation, the solution to the elliptic equation can be done variationally, right? So in fact, if you want to look at the solution to this elliptic PDE, you can actually just consider the minimizer of this variational form, and it's actually a quadratic form. So in a way that in order to capture the behavior of the solution, we can also just capture the behavior of the energy form, which is a quadratic form, on every scale. So that's like a way of doing renormalization, is that we define some energy quantity at every scale, and we show that, first of all, they are approximately additive. And then at every scale, we have an energy quantity, which we also associated with this A of that scale, which is some kind of effective covariance at that scale. So that came from the energy, but it's also a way of doing coarse graining or renormalization if you move up the scales. And of course, a central question arises is that you want to do it quite precisely. You want to capture what is the rate of convergence. You know that these quantities are subadditive, so they will converge to some limit, but you also want to capture the rate of convergence. And that's typically done by using some kind of mixing conditions. And of course, in the original work of Nadav and Spencer, and also in the work of Gloria Otto, they have assumed some spectral gap condition so that you have a rate of convergence. But that assumption is often too much when you're working with systems on an infinite volume. So in fact, what we did with Paul is that we make use of the so-called second order equation. So what does that mean? So in order to show the mixing, we want to show that if we change the field a little bit in the faraway box, it will only affect the energy quantity here by a very small amount, right? So how do we do that? So in fact, if we start with the original Helmholtz-Thurstrand operator, which has a lot of terms, but we can actually see that for beta large, the leading term is this Laplacian term. And the rest term is actually much smaller than the Laplacian term. So we can actually borrow the idea from PDE. There is something called the Schauder theory, which tells you that at beta large, the solution can be quite well approximated by harmonic functions. And there will be so-called the C0 1 minus epsilon regularity, which telling you the Green's function decays as if you're in the Green's function for the standard Laplacian, but except by a difference of the power epsilon. And this epsilon is actually, you can get better and better if you send beta to infinity. Now, in order to show the mixing, we can actually start with the Helmholtz-Thurstrand PDE. Then we took the partial derivative of the field. And then we look at this new quantity, which is the partial y of the Helmholtz-Thurstrand Green's function. In fact, this new quantity solves a new equation with a more complicated operator there, but you can see that the more complicated operator still has the leading term like a Laplacian plus the productive term. So you can also apply the so-called the Schauder type of argument to get the regularity estimate. So in fact, you can get is that the Green's function that after taking this partial derivative, which I call the second order Green's function, is actually have better regularity than the initial Green's functions because they have, or they are kind of living in higher dimensions. They have 4 variables, x, y, x1, y1, and the regularity estimate was telling you that you can actually analyze the gradient and mixed gradient of that, and this should be 2D, there's no -1 here, but so you can actually get at least a power law decay of the second order Green's function, and that power law decay of this quantity will tell you about the mixing of your original energy quantities. And that's how you run through and getting the rate of convergence to the limit. And of course, so this was used in our work to find the asymptotic expansion of the two-point function. And for the question of the parallel spin wave, we need a more precise estimate for the decay of these second-order Green's function. In fact, we want the optimal decay in the sense of removing the epsilon, and in the sense of replacing L2 by NALP, in a sense. Okay, I guess that's it. That's all I want to say today. Thank you.